Okay, I press start.
Yep.
Live.
All right, guys, it's 2 o'clock. Hello, everyone. It's 2 p.m. here in Singapore, and we are live now. So welcome. As a General Manager of GESTRA Asia Pacific, my name is Hedda Herman, and I would like to welcome all of you to our GESTRA's first webinar. As you know, this is our first webinar in a series of 3, and I sincerely hope that you will join us for additional 2 seminars that we will be holding during the month of June. Today, we are anticipating in a very large number of attendees, and we're estimating about close to 1,000 attendees. So I hope technology works very well wherever you are, but we are anticipating close to 1,000 attendees across Asia Pacific region, including Pakistan, India, Southeast Asia, Korea, Japan, New Zealand, Australia, and all the countries that they're in between. So welcome everybody. Before we start, I would like to share some session guidelines. This session will be recorded and it will be available after this session. So we will be happy to distribute a copy of this recording. Also, during this session, attendees will be muted. This means you will not be able to speak. We will not be able to hear you. However, during the session, you are encouraged to write any questions you might have. So feel free to feed questions, but please do include your name that we know in case we don't get to answer your question, that we are sure to get back to you after the session with the answers. So feel free to send questions during the session, but we will answer them at the end of this session. And in case we don't, then we'll follow up later. Yep. So now I would like to introduce today's presenters to you. We have with us our experts from Germany. We have Marcel Meyer and we have Heiner Tweitmann, which both of them will introduce themselves later at the time of their session. And also now briefly, because we have a very large audience here, so briefly for the audience that don't work closely with GESTRA, I would like to just briefly show you the footprint of GESTRA's global presence. As you can see, we remain to have our main manufacturing facility in Germany, Bremen, Germany. We have 10 direct operating company across the world, and they are listed on the left-hand side, as well as we continue to operate through distributorship model, and we have a representation in 75 countries. If you have any further questions about GESTRA details, we're happy to follow up with you after this session. So I would now turn over to our next speaker, Marcel Meyer, and he will introduce himself and he will take you through a first topic on steam traps and types of steam traps.
All right. Yes, thank you very much, Hedda.
Sure.
Just give me a second. I will open the presentation now for everyone to watch so that we can have this experience together. Just give me a second. All right. So share my screen.
Yeah, here we are.
Okay, let's go that way. So yeah, it's Marcel Meyer. I'm a specialist for steam and automation technology for the company GESTRA in the headquarters in Germany. And yeah, we are offering trainings all around the steam business and boiler house automation technology. And yeah, we are offering a lot of trainings around the very basics of steam up to, let's say, the more challenging parts of a steam installation, how to troubleshoot in case you run into problems, and how to, let's say, make your system more efficient. So this is our challenge. And this is why we usually offer presence training. So we are traveling around the world trying to make a sufficient training for everyone who would like to have some information about the STEAM business. But today we have to change a little bit our common way of presenting to this kind of webinar here. So we hope we can transfer a lot of our knowledge to you and that you get a first very good impression out of, let's say, the basic of steam traps. So this will be, yeah, more or less the foundation of our webinar that we have here. We will talk about the different kinds of steam traps that we have, the more common ones and the ones that are not so common. And this will be the first part of the webinar, and then right after that we will have a second part with the so-called total cost of ownership for different steam traps. So what do they cost during the whole time of operation, which is yeah, something that will directly refer to the first part of the presentation.
Marcel, deine Kamera umschalten.
Yeah.
Yeah.
Not possible. Okay, I have to do that just now. Okay, I guess you would rather like to see me. So this is why I will now maybe change to a different way of showing it. So just give me a second. All right. So.
Marcel, you
So,
also
hello?
need-
Yeah,
Okay, good.
hello.
Now you can see my face.
Good.
Yes.
Perfect. All right. So steam traps are yeah, almost everywhere. As soon as we want to use a specific source of energy to heat up a product or to maybe sterilize something, we will need, of course, a source of heat. And for us, it's steam. Steam can carry quite a lot and quite a high amount of heat. And we want to use that heat in a heat exchanger to just transfer the so-called heat of evaporation to the product. And as soon as we did this in the heat exchanger, we will have a so-called phase transition. So the steam that I put inside the heat exchanger will start to condense and become liquid again. But we don't want to have, let's say, the liquid remaining in the system. The liquid should be drained out of the system so that we only have steam, because only steam has this very good heat transfer properties that we would like to have so that our system works sufficiently. And you have this different kinds of applications almost everywhere. You can take a look on hospitals, for instance. They're using steam to sterilize the tools for the operations. Or we have the food and beverage industry, where we have heat exchangers to heat up, for instance, milk or beer or whatever you'd like to heat up to make it tasty in the end. Also there you need steam traps. We need a lot of steam traps also in the chemical industry for different kind of processes. So you almost find them everywhere. And if we think about steam traps, we have to think about the different requirements that we have. So you could divide it into two different parts. We can speak about the very basic requirements. So the things that a steam trap really should fulfill. Without that, we cannot guarantee that the process is working in the most sufficient way. And we have two very basic requirements that we really have to guarantee. The first one is to discharge the condensate without the loss of live steam. We had to use fuel, or we had to burn fuel to create our steam. This fuel can be very, very different. We could have oil or gas, or we could have biomass or electric heating rods. It depends. But that tells us, okay, I had to use something that cost me money to create my steam. And this makes steam have a price. And if I just put this steam that I have just through a steam trap without making use of it, I'm losing quite a lot of money. So this is a very basic thing that we really have to guarantee. We have to discharge only the condensate without a loss of live steam. And the second very important requirement we have here is the automatic air venting. As soon as I shut down a system and it is not pressurized anymore, air has the possibility to enter the system. And if that happened, the air will remain in the system as long as I didn't bring it out. So I have to bring it out of the system to have a very good heat transfer rate, because air prevents the heat transfer, and it does it very well. So if you think of your radiators at home to heat up your rooms, your living room, if you have air in your radiation system, then you will have a very cold surface, and this cold surface might be not the right way of not the right functionality for your radiator. So we have to get it out. And also this task will usually be done by a steam trap. So they're not just dividing steam and condensate, they also have to divide steam and air, which is sometimes a little more challenging because they both are at the gaseous state. So not this easy to differentiate here. So these are the things we have to do. And we also have the additional requirements. So the things that are, let's say, nice to have. So it would be very nice if I have a heating process, if we have no banking up of condensate. Some steam traps have no banking up of condensate. So every amount of condensate coming to the steam trap will be discharged immediately. Some other steam traps do have a little banking up of condensate. It's just part of their working principle, so it's just normal. But that tells us, okay, they have a different location in the steam system. They have to be installed somewhere else and not directly in the heating process, because we don't want to have a banking up of condensate in the heat exchanger, because this will prevent the heat transfer and we cannot heat up the product anymore. What other things can we say? Steam trap should be suitable for pressure and flow rate fluctuations. For instance, if I start up the system, we have a lot of cold surfaces all around. It's the pipelines which are cold, it's the heat exchanger vessel which is cold. So in the very beginning, we will have a lot of condensation. So the steam will condensate on each and every surface, and the amount of condensate is quite high. But after a while, when everything is heated up sufficiently, then the amount of condensate will drop down. And that tells us that a steam trap has to be able to handle different amounts of condensate and also different pressures. Because when I start up the system, the pressure in the beginning is rather low, but it's increasing, and they have to control it more or less. Some steam traps can do that very well, and some might have problems with that, but we will see the difference here. And what also should be very nice, especially nowadays, is the easy to install requirement that we see here. In the past, it was very hard with the design of older kinds of steam traps to install them in the pipeline, because of the design of the body and so on. And today we change a lot of things of the design so that it's very easy to exchange them, and this will decrease rapidly the maintenance time that I need to exchange one of the steam traps, for instance. So the downtime of the system is much lower. Yeah, unaffected by dirt, for instance, it's also very important. Dirt is in almost each and every steam system. This could be, let's say, grease or little pieces of paper. If we have a paper mill where we want to heat up the machine to create our paper, and or we could go to a steel mill. If we create steel, we could have even little steel balls in our pipeline which travels through the system, and of course you can imagine if a little steel ball is blocking such a steam trap, this is not fine. So some steam traps can handle dirt very well and some don't. We will see how that works. Yeah, frost-proof is also a nice thing to have, but it depends on the ambient conditions that we have and where we are located on the planet. So this is, let's say, our typical steam trap range that we have. These are, and you can differentiate them very easily. They even look similar here. So you see the two here on the left-hand side. These are so-called thermostatic steam traps. And we have a bimetallic steam trap here in this part, and we have a membrane type steam trap, a so-called MK, here in this part. So these two can be clustered as thermostatic steam traps. We also have a ball float steam trap, which is, let's say, the most sophisticated one. So it has a very good control function and a large body, which makes it have a very big capacity, so it can discharge high amounts depending on the design a little bit. Yeah, we will speak about that one, of course. Then we have another one, the thermodynamic steam trap, which is, I would say, the most common steam trap on the world. I would say around 50% of all steam traps on the world are thermodynamic traps. It depends a little bit in which country we are. This has one very simple reason. Thermodynamic traps are the cheapest ones. But when we think about these kind of steam traps, we have to consider the two basic requirements. So when we think of the loss of life steam, which was the first one, and the automatic air venting, we might get problems with such a design. So this kind of steam trap is only, let's say, suitable where steam doesn't really have a price. But as soon as steam has a, let's say, a certain price, then we should not think of this kind of steam trap. But then the other ones go into operation. All right, so the principle of a ball float steam trap, which is the first one we are taking a look on, is rather simple. So we have a condensate inlet, we have a ball float, and we have a condensate outlet. And the level, the water level, which will increase by appearing condensate, will sooner or later lead to a lift here of the plug. And the plug is lifted then, and the orifice is open, so the condensate can be discharged. It's a very simple principle, and here we have a first very big advantage of this kind of design, because we have here the plug and the seat in the water area. This is one of the best things to guarantee that we don't lose any life steam, because this is something that is known as a water lock. So very similar like we have it in our bathroom. This kind of siphon that we usually have is also some kind of water lock that we need to guarantee that we don't get any gases from the canalization in our bathroom. And here the principle is, let's say, similar. As soon as we have a water level, steam cannot travel through it. But this is only, let's say, a principle. If we take a look on the design, how it nowadays looks alike, we see here how the principle works. So condensate is entering, it gets more and more, and the higher the level goes, the more of the orifice will be opened. And then you see how the condensate will be discharged here. And here we see a very specific phenomena now. So as soon as we have this very hot condensate being reduced in pressure, we will create so-called flash steam. So after the steam trap, when it opened, we will not have only condensate, we will have condensate and small amounts of steam. But these amounts of steam are not this small because they have, let's say, a big volume, and this big volume steam has to be able to go to the condensate line, which is the reason why we always recommend to design the pipeline here downstream the steam trap big enough so that the flash steam can leave the steam trap. And here with the design, you already see that a ball float steam trap is very much unaffected by dirt, because we have a lot of room here, a lot of space, so that dirt will not affect the operation. This is a valuable thing, especially for dirty processes where we usually know, there's a lot of dirt inside, we have to change something. But here we have a lot of space for that. Yeah, here's some more details about it, and I have to tell you what are the two basic requirements that we have on a steam trap. So the first one is we have to discharge condensate without losing life steam. So this is what this kind of control unit guarantees. As soon as we have the water lock here, steam cannot leave the steam trap. But the second basic requirement was the automated air venting. And yeah, as you can imagine, air venting is not possible if we take a look on this kind of design here, because the air will always stay above the water line and cannot be discharged. But we have to get rid of it. We don't want to have it in the process. So with this design, we need something that helps us out. And we did it with this little capsule that we see here attached to the control unit inside the ball float steam trap. So this is a little membrane type capsule that we also use in our MK, so our membrane type steam trap. And this is the part who will guarantee for us, okay, we have the automatic air venting as part of the steam trap. So as soon as we have air here in the body of the steam trap, the temperature will drop because of the low heat transfer of air. This membrane detects this temperature drop, and if the temperature is too low, it will open, and then the air will be discharged to the condensate line, and we don't have it in the process anymore. And if we have reached the steam temperature again, this one will close, and then let's say the control unit will go back into its common or usual operation. Very simple design, which works fine. Okay, we can get a lot of information by taking a look on the nameplate. Each and every steam trap has a nameplate attached, and sometimes we don't really know what do we have inside here, but by the nameplate we can figure that out very easy. If we have a GESTRA ball float steam trap installed, then we are speaking about a so-called UNA. So it's a UNA ball float steam trap of the 4 series. So it's the new series that we have in operation. The 6 tells us the pressure rate of the steam trap, and then we have 2 additional letters right behind it. The H tells us something about the flow direction. So it could be H or it could be V. H stands for horizontal, and if we take a look on the picture before, this is how a horizontal flow direction looks like. So it's just this way. So it goes from left to right. But we can change it if we like. We can change it to vertical. So we just have to loosen 4 screws and another 4 screws here on the control unit, and then we can turn it 90 degrees. Then we can fix it again, and we changed it from horizontal to vertical flow direction. And what was, let's say, the original installation, you can see here on the nameplate. So this was horizontal installation, and the second letter we see here is an L, and this L stands for left, and it tells us, okay, it's horizontal left, so the flow direction is from left to right. We could also have the opposite way, so there would be an R, we could go from right to left, and this will change the, let's say, where we find the body of the steam trap. So here we have the flange body, and if we have maybe a wall on this side and we cannot install this kind of steam trap here, then we can change, let's say, the body part on the other side of the steam trap. But you cannot do this on your own, like you could with the flow direction from horizontal to vertical. This is something that has to be ordered because the design looks different here. So the part is a little bit different, but then you also have the possibility to have this body on the other side. So we will have a part number here at this part, the manufacturing date. So when was it produced? We will have the maximum differential pressure for that kind of steam trap, and this here tells us what's about our control unit. Does it have this automatic air venting capsule attached or not? If it has this capsule for air venting, then it's called a duplex. If it doesn't have that, then it's called a simplex. So here we're speaking about with a membrane attached, so we are fine. We have here like a so-called QR code, so data matrix code, that gives us some information about, okay, what's the control unit, the original control unit of this device, the part number, and also the day of manufacturing. So we get some information from here just to figure out, okay, maybe for how long do we have it in operation? What were the test results when we tested it in our production? We have 100% testing. So each and every ball float steam trap, UNA, will be tested, 100% testing. So we put pressurized air of 60 bar on the entry side, and we pull a vacuum on the other side, and the vacuum has to be stable, and only then we, yeah, let's say sell it and ship it. Yeah, but as you can imagine, we have quite a lot of material with such a ball float steam trap, but it is always, let's say, the most sophisticated and the best steam trap for each and every installation, because of its way of working. We don't have any banking up. The more condensate we get inside the steam trap, the more opening of the orifice we will get. So it is controlling in a way, which makes it, yeah, let's say suitable for heat exchangers, for instance, but also for streamlined drainage if we don't have that much space. But of course, because of the lot of material, it's compared to the other ones, not the cheapest solution. So we had to change some things, and we created the so-called UNA 1, which is a ball float steam trap, but the design is a little bit more simple. So we have here the advantages of a ball float steam trap. If we take a look inside, so we have the ball float and the rolling ball valve here at the outlet of the, let's say, outlet of the control unit to the condensate line. And then we have here a conic connection, and then we press the control unit here on this conic connection, and then we have a fully functional ball float steam trap with all its advantages, because we also can attach, let's say, an air venting membrane here above. Okay, so that was it so far for the ball float steam trap, but we want to take a look also on the other ones. And if we take a look on this kind of steam traps we are seeing here right now, we see a very specific design. All of them are rhombic in its shape. And this is what gives us the information. Okay, this is why we had to design it that way, because of the easy installation requirement we spoke about earlier. And here we can see different kinds of steam trap. The thermostatic ones, they have this very specific design nowadays, and we want to go more into detail to these steam traps. This is what I mean. So to, let's say, when it comes to easy installation, in the past we had, say, a body of a steam trap which was squared, and it was not possible to access the screws here in the flange connection. So there was only one way to exchange the steam trap if it had to be replaced. You had to use a saw, and then you had to saw the screws, and only then it was possible to exchange it. But now it's much easier by just yeah, taking out the screws that way. Okay, so the second type of steam trap we would like to take a look on is the so-called BK. This is a bimetallic steam trap, and it works with this bimetallic stainless steel plates that we see here. So what we have is are two different kinds of stainless steel, and we welded them together. And then we have one of these plates you can see here, and as soon as we have an increase in temperature, they will start to bend. And what we did is we counted these kind of stainless steel plates against each other. So as soon as we have an increase in temperature, they will lift up the stage nozzle, and they will then and the stage nozzle will be pulled inside the seat, and then it is shut, totally shut. So we have the entry of condensate coming from here, then we go through the strainer and then here to the control unit, which will sense the temperature, the current temperature. The strainer itself should be cleaned every now and then. So this is something that we recommend in the manuals. You only have to put a wrench here at this at the screw. You have to loosen it, and then you can put the strainer into citric acid, and then it is fine again for another year. You don't have to do it, but we recommend to do it because this can double or triple the lifetime of a steam trap. But if we think of a BK like we see here, we have the very big advantage that the lifetime of such a BK, bimetallic steam trap, is rather long. So if we have, let's say, a BK 45, depends a little bit on the pressure we are operating here, but it could last for 15 years. This is possible, up to 15 years. It depends a little bit on the condensate quality and whether we have dirt or not. This is something that we have to admit. Okay. Yeah. How does it work? I want to show you this diagram here. And this diagram shows us three specific graphs. So we have here the red line, and the red line is the so-called saturated steam curve. So at this temperature, which is on the left side, and pressure, we are at saturation steam temperature. So, for instance, if we have 1 bar absolute, so ambient pressure, like we have maybe today outside, then we can increase the temperature of the water. So below the red line, we are in the water area, and we can increase the temperature just by using some kind of fuel or putting it in the oven. And as soon as we reach 100 degrees Celsius, we are at saturation temperature. So now we can create steam. We only have to guarantee that we are at 100 degrees Celsius. And now we can see the more I increase the temperature, the pressure, the higher is the saturation temperature. And then in the end, so we have a curve here in the beginning on lower pressures. And if we go to higher pressures, we go into, let's say, a straight line. The curve is only on low pressures. So why do I tell you that? Because I want to show you the two lines below the red one. Because these are the opening characteristics of the two thermostatic steam traps, of the MK, which is the blue one, and the BK, so the bimetallic one, which is this green one. And you can see that the opening lines are in the water area. So we have to cool down the condensate, which will reach the steam trap a little lower than saturated steam temperature. So then saturated temperature, maybe 1 or 2 Kelvin below that. And then the steam trap will, let's say, be tight and be shut as long as we haven't not subcooled the condensate to this temperature. And for an MK, this is, let's say, 10 Kelvin below saturation temperature, 10 Kelvin. And compared to the BK, the bimetallic one, it has to cool down at average 20 Kelvin, roundabout. So we have to subcool it for 20 Kelvin, and then the steam trap recognizes, okay, there must be condensate, there cannot be steam, so I have to open. And then the temperature in front of the steam trap will increase again, and 1 or 2 Kelvin before we are back at saturation temperature, the steam trap will close again. So with that, we guarantee that we don't have any loss of live steam. Yeah, so you see now the working principle. We have here the counted bimetallic plates that we see here, and this will now lead to the lift of the control unit. And here you can see now that it is tight, so we have high temperature, close to saturation temperature, and now we have the condensate that needs to cool down before around 20 Kelvin. It needs to cool down for 20 Kelvin before these bimetallic plates start to become weak again, so that the bending is not there anymore, and it will open the orifice, and then it will discharge the condensate. Yeah, what we have to, what we kept in mind when we think of the design was that we want to increase the lifetime of such a steam trap, because we want to have it in operation for as much time as possible. So what we have here is a multi-stage pressure reduction. So we don't only reduce the pressure on one seat, we have 3 chambers right after each other. So the first one is the little chamber here, where we have the first pressure reduction. So we will have here some small amounts of flash steam and condensate appearing here. And then we have a second chamber where we have more flash steam. And then we have a third chamber, which is in the body, which will, let's say, reduce the rest of the pressure. which we have here. So a 3-step pressure reduction, which is the best way to go here. So this is how an all-new bimetallic regulator or controller looks like. They have here on the top a red color. That tells us this is, let's say, the standard version of a bimetallic controller, because yeah, this is set to 20 Kelvin subcooling, because when we are producing them in a room that is temperature controlled all the time, so that we can do it very, very precisely. But we could change something just by changing, let's say, the drilling here. So we can turn the stage nozzle, and by turning the stage nozzle, we can come closer or get more far away from the saturated steam curve that we see here. So on the first picture it was red, now it is blue, but this is the saturated steam curve, and this is the opening characteristic of the bimetallic steam trap. Unfortunately, bimetallic controllers usually have a linear characteristic, a linear opening characteristic. So this was the reason why we could only use bimetallic steam traps on high pressures. So when we are have more than 10 bar, then we could only use bimetallic. But we also want to have the advantages of a BK on lower pressures, which we have here. But we had to do something to, let's say, realize a bending of the opening characteristic, like the saturated steam curve does. And we did this with this very specific shape of the stainless steel plates that we see here. And with this design, we have on low pressures only 2 connection points. So only this one and the one on the opposite. So this will then lead to low operating forces, which makes, let's say, the opening characteristic, yeah, still being linear, but with more inclination here, with a higher inclination. If we go to higher pressures, then 2 more connection points go into operation. So it's that one so the other one's on the opposite side, and then we have after 8 bar, 10 bar. We have all the connection points, all 8 that we could have, being touching. And then we have, let's say, for the rest of the saturated steam curve, the linear characteristic, which is all fine because the saturated steam curve will also go into a linear characteristic. So this is how we manage to have such a curve also on, let's say, lower pressures for the bimetallic steam trap. So I told you about bimetallic steam traps are very much suitable for high pressure applications. This is how a BK looks like when we go, for instance, to power plants, where we could have pressures up to pressure rate PN 630. So this kind of steam trap will work to maximum pressures of 300 bar, which is quite a lot, and up to differential pressures of 250 bar. So if we have, for instance, a turbine and we want to drain the turbine, we need a, let's say, a very good steam trap who can handle these conditions. And this is a BK212 who is able to operate at very high pressures and very high temperatures. So this can go up to at least up to 580 degrees Celsius. So, and also for superheated steam. And so on, so the typical power plant application, or where we have very high pressures. So it's, I would say, the most robust regulator for tough conditions. It also works on superheated steam, which is typical for BK. So usually also in power plants, it can. It has the automatic air venting because it's a thermostatic steam trap, so it detects colder temperatures. So also when air is in the system, it will detect it and then discharge as long as we have not reached steam temperature. Installation in any position, so we can have it in vertical and horizontal installation, which is very good. The stage nozzle works as non-return valve. If we might have a backflow of condensate to prevent this, we will have a non-return valve integrated. So there, a BK is typical for steamline drainage because we have a little banking up of condensate on thermostatic steam traps. And the BK has a little more than the MK. So we are having, let's say, a little banking up in the drainage line. And then it will discharge again, and then it will bank up a little bit. And this is okay if I have a steamline drainage with enough space to the steam trap, so that I can allow myself this little banking up of, okay, it depends a little bit on the process of maybe 1 or 1.5 meters. Depends, as I said. But we should not use it on heat exchangers. So here we have the membrane type steam trap. So it's an MK45 with the membrane. It's the same membrane, as I said, on the control unit of a ball float steam trap. So it's another thermostatic one, which is also capable of doing the air venting very well. And if you take a look on the body of the steam trap, it looks very much like the BK, like the bimetallic steam trap. Only the top of the body is a little bit different. It's flat compared to the BK, which has, let's say, a different shape, but the body itself, it looks similar. And so the condensate also travels here through a strainer here to the membrane, to the capsule, and it shall now detect the current temperature, and by the temperature it will discharge the condensate. So this is the opening curve of the MK. It has average 10 Kelvin subcooling compared to the bimetallic one, which had 20 Kelvin. So it's closer to the saturated steam curve, which makes it opening and closing more often. So it will not have this much of banking up. The banking up is much less, but we still have it a little bit, but it's okay because we need this banking up of condensate. So because with this banking up of condensate, we can guarantee that the steam cannot travel through it. So it's always above the water line, which is then the guarantee for not having a loss of live steam. So, and how does it work? The design of such a capsule is simple but genius. We have 3 parts. We have an upper part, which you can see here. We have a, we have a down part, a lower part, like we can see here. And we have a membrane inside, made out of Hastelloy. And here we have a plug. And the parts are welded together at this part here. And between the upper part and the membrane, we will have a liquid. And this liquid is water with small amounts of alcohol. And here in this situation, we will have here this water alcohol mixture being a liquid state. So now the steam trap is open. But as soon as we come close to the steam temperature, to the saturation temperature, this water and alcohol solution will evaporate a little bit before the steam temperature because of the small amounts of alcohol inside. So then we will have here the evaporation. We increase the volume, and with this increase of volume, we will create pressure, and this pressure will press the plug now on the seat, and now it is tight. So it's shut. The steam trap will not leave any steam, and now the banking up starts. It's not much. It's only 10 Kelvin roundabout, and then after a while, this liquid, this vapor we have here, the steam alcohol mixture, will start to condense. So we are then losing the pressure here, and then we will have the membrane which will pull, let's say, the plug from the seat, and then we can go ahead with the working, because then we will discharge the condensate. So this is very much how it works. But there are only there are 2 different designs of capsules. The one that we can see here has a flat seat. So it's one flat seat, and all the pressure will be released via this seat. But we also have, let's say, a different kind of capsule, which we can see here. So the capsule is here, and we have here the so-called tandem seat, and you already see how it works. So it's here the flat seat that we just saw on the pictures before, and we added an additional plug, like we can see here. And if now the steam trap starts to close, then on the first situation is that the plug falls into the first seat, and now we don't have any mass flow anymore. And then the second seat comes down, and the second seat can close without any flow, without any velocity here, which will guarantee that we have no wear here at this part, so this surface will be fine all the time. So this additional plug here is very good if we want to increase the lifetime of such a membrane. So it's also to let's say reduce the wear of this steam trap. If we take a look on such a membrane from above, then we can figure out a lot of information. So the first letter that is stamped in here is 5, and this tells us something about the pressure range. So this capsule suits to up to 32 bar differential pressure. And if we have for the second letter, the N, this is the standard capsule with the 10 Kelvin subcooling. But we could also have different kinds of capsules here. Also an H is possible. Then we only have a subcooling of 5 Kelvin, so we are closer to the saturation curve. Or we could have a U, which means for the undercooling capsule, then we are much far away from the saturated steam curve of 30 Kelvin. How do we manage that? The liquid, the mixture is a little bit different. So it's a different kind of alcohol then, and the amounts differ a little bit. So this is how we can manage that. Then the third letter that we see here is either a 1 or a 2. The 1 stands for, let's say low capacities, and it has the tandem seat with the additional plug we just saw on the picture before. So with this plug, which will guarantee an increase of the lifetime, but this design takes a little bit of the capacity of this membrane type steam trap. It's not much. If we speak about only the flat-seated version of an MK, we can discharge, let's say, 400 kilograms per hour. If we think about the tandem-seated version, we can discharge 350 kilograms per hour, roundabout. So if we have the 2 stamped in here, we will have the single-seated version. Here on the other side, we will have the manufacturing date. If we need to know it, also might be a good idea to know how long this might be in operation here. So the MK series is very good when it comes to air venting. So the air venting part of it is very good, and this is why we also attached it to the UNA, to the wall float steam trap, because it reacts in the fastest way. It's very sensitive because it is rather close to the saturated curve, and you can also install it for in horizontal and vertical situation. And this is also typical for streamline drainage. So the MK series, where we have them and we don't have that much space, maybe, then I would rather recommend the MK because it doesn't have that much of banking up. So it's very sensitive, as we said. So yes, let us speak about the thermodynamic type of steam trap, so-called DK. And it works very simple, I would say. Here's the condensate inlet. It also travels through a strainer, and then all the magic comes from this valve disc. And this valve disc has the size maybe of a little coin that you use for paying. And here's the outlet, and it works with the so-called Venturi effect. And it's the same working principle for an airplane that wants to start. This now sounds very special, but it's rather simple. If we speak about the Venturi effect, it tells us if we have slow flow velocities, then the temperature, the pressure is higher, If we have fast flow velocities, then the temperature, the pressure is increasing. So high flow velocities, low pressure, low flow velocities, higher pressure. So this is very much how it works. We have here, let's say, the condensate traveling through the steam trap, and the condensate travels at the speed of half a meter per second up to 1 or 1.5 meters per second. This is slow enough so that the valve disc will be lifted up, and then the condensate can be discharged. If now steam comes to the steam trap, which should be blocked, this steam travels much faster through the system. So it's an average, I would say, 25 meters per second. So as soon as we have now here steam traveling through is passing here the valve disc, we will have increase in pressure, and then the valve disc will be pulled on the seat here, and then it is tight, shut tight. Then the steam bubble, which will be here, first has to condense. So it has to become condensate again, and only then it is possible to open again when condensate comes to it. And here we see, we think of the two basic requirements we spoke about in the very beginning. The first one was we don't like the live steam losses. That was the first one. And here we have, let's say, the first little amount of live steam that we're losing because we need this high flow velocity here, so that the valve disc can detect, there's steam, so I have to close. This is not this much of live steam that we are losing here, but we don't want to have a steam trap that is losing any live steam at all. The second disadvantage is that we have here a metal-to-metal seat. So if it goes, if it's clapping always on the seat here, you will have not the good surfaces after 1.5 years, for instance. After 1.5 years, you will not have, let's say, if we have any dirt particles or anything else, we have little scratches here on the valve disc, and then we might lose some live steam, what we really don't want to do. If we have air in our system, this was the second basic requirement, air travels through the system rather as fast as steam than as condensate. So it's also at, I would say, 20-25 meters per second. And that, what does it tell this steam trap? So as soon as we have air, the air will also flow as fast as steam, and it will tell the steam trap to close. And this is what it's doing. And then we have a little air bubble here on top of the valve disc. And and let's say air bubble doesn't condense. So as soon as the steam trap got in contact with air internally, then it will be blocked for a very, very long time. So as long as the air has not disappeared, maybe here via this thread, or that it is condensed somehow, or maybe through small leakages because this is damaged or something like this, this steam trap will be closed. So also the second basic requirements is not fulfilled sufficiently with this kind of steam trap, but it is cheap. So this is then something you have to, let's say, wait out. But if you want to have a proper working steam system, I would not recommend this kind of steam trap. So this is a very common kind of steam trap we find very often, for instance, in the United States. The design is similar to the very first steam trap that was invented in the 19th century. And yeah, it's a so-called inverted bucket steam trap. It works rather simple. So we have here the entering condensate, which will lift up this bucket here. Or it will not lift up this bucket here, only steam can do it. So if the condensate travels through here, it will just go this way, and then it can be discharged here via this closing unit into the condensate line. And as soon as we have steam appearing, then this little bucket will be lifted up, and then we have the connections here, and then the plug will be pushed inside the orifice, and then the steam trap is closed. But here you see, let's say, the first disadvantage we have. So if we have a closing here in this steam area, it's much harder to make it close tight so that it don't have any steam losses. It's much easier to shut a steam trap when it's in the water area rather than in the steam area. And the second problem might be what's with air. So if air comes to the steam trap, the bucket will be lifted up and also be closed. That's the reason why we have to do something, because also the air would not disappear from the bucket. It will stay here and will always, let's say, swim above the water line, which will keep the steam trap blocked. But to make this work, we have to do a little drilling here, and this little drilling will allow, let's say, the air to leave if necessary. But this then is also, let's say, a very small part where we can have steam losses. So this is, let's say, a good steam trap when it comes to, let's say, the working principle, because we have no banking up of condensate, because it's a float principle we have here. But we have the disadvantages of closing in the steam area and the problem with the air venting. So this is the last steam trap I'd like to speak about. It is so-called the fixed orifice steam trap. Fixed orifice steam traps are, let's say, not this common, but they start to make their way inside steam businesses, but they have quite a lot of disadvantages. We'll figure that out when we think of the working principle. So the condensate inlet is here, and then it travels through a strainer, which is very good because all we have with such a fixed orifice steam trap is this little hole here, the drilling. And this is only one diameter, always the same little small diameter. And here we have the condensate outlet. So if we wouldn't have any strainer here, we will get any, of course, problems every now and then, because little dirt particles could block here this very small orifice that we have here. And yes, so the disadvantage here is that this will only work for one very specific condition. With a, I would say it's 1% more or less is also fine, but then it won't work anymore. So it's only working for one amount of condensate and one pressure. As soon as we change just small things about it, it won't work anymore, not in a sufficient way. So if we have condensate coming inside the steam trap, the condensate is rather dense compared to the steam, so it can travel here through the small drilling. But as soon as we have steam has a high volume, it cannot pass this easy through this drilling. So it will stay in the system while the condensate can be discharged. But we still have the problem with the air venting, because air also has a very high volume and it can also not fit through it. And as soon as air can pass through the hole, then also steam will follow directly after that. So this is a design that doesn't have any control. So each and every other steam trap have a control function. They operate at different pressures and different temperatures with different amount of steam of condensate amounts. And this one is only for, let's say, one fixed condition, but it you never have it. If you have just small changes in pressures, which could be possible just by changing one part of your steam system, you will run into problems with that one. Okay, so that was all from my side. This was, let's say, a very fast but broad overview about different kinds of steam trap and how they operate and where to use which one. This is, let's say, the basic knowledge that we need for the next part of the presentation now, which will now, let's say, hand over to my fellow colleague, Mr. Heiner Twachtmann, who will tell us something about the total cost of ownership about the steam traps. So just give me a second. I will I have to change the presentation now.
Thanks, Marcel. That was really good. I hope our audience still enjoying it. And so over to Mr. Heiner.
Yeah, just.
Okay.
Just give me a second. All right. Yes, Hannah, you can start if you like.
Thank you. On the camera, you can also change.
I did, so I can see you and also your
Okay.
presentation.
Okay, but I cannot see me, but that's no problem. So, dear audience, thank you very much for listening. I hope you enjoy it over in the last 60 minutes and you doesn't need a break now, because we are sitting all at home. It's easy to go to the toilet and something like that. So I will go on with the next part of our seminar today. And just to introduce myself, when I was becoming a marine engineer, because Bremen is close to the seaside and the ships coming up the river here, I found it very interesting, and so I decided to become a marine engineer. And of course, on each ship you will find steam to heat up the tanks that the heavy oil is able to flow to the machine room, but the water hammer at that time was already heavily, and a lot of steam trap were already broken by these water hammers, and that gives me the first contribution to steam. So I later on come to GESTRA in 1984, and when I calculate correctly, it's more or less 36 years now, and I find it's like 10 years because the job of steam is really interesting and offers you a lot of different opportunities, and the training later on I had to do since 2003 when I became the GESTRA Academy manager was really also a very nice option to say this was the right way to do it here and to give my knowledge to the next generation. Well, when we go, next slide, doesn't work. When we talk about our founder, Gustav F. Gerz, who founded the company already 118 years ago, means that he gives to us a nice believing that energy must become very worth to the world. And when I listened to Marcel just before, I find already in many of his words that he is trying to fulfill this thinking of Mr. Gustav F. Gerz today. Because German quality doesn't only mean to produce cars of high efficiency. And the last 60 years, we have looked always to new opportunities for safer technique and valves and very long lifetime and solid working principle for our items. And still today, the GESTRA delivery program, you will find valves which, because of their reliability, have a working principle was already done 50 years ago. If you look for the capsule, for instance, Marcel just explained very well, it was already founded in 1960, that is 60 years ago. Or the radio station also valve, which we use under pressure difference up to 560 bar in the power plants, are now 60 years old. And all these are really reliable valves, which we have in our delivery program now. Looking for the historical steam traps, already the first GESTRA designed steam traps were different to that of all competitors. While many processes use only this kind of orifice of steam traps or stop valves, where operators have to change the setting and closing and opening valves during the process regarding the amount of flow, GESTRA already sells the optimizing steam traps, and this old picture here from 1915 shows the principle of the self-regulating plates using the flashing out of hot condensate, the flash steam, which Marcel explained before, and this was the self-regulating up to 70% of the complete range of the steam traps already. And I think that was at that time already a large, a very big advantage what we have done in that time. Well, we have now listened 1 hour regarding the principle of the steam traps. We have to say that more or less we must talk when we talk about the operating cost, leakage of steam traps. We know that this has, over the whole lifetime of maybe 15-20 years, the bore-fluid steam trap, no problems with leaking of steam. Well, we don't consider at the moment dirt or any water hammer problems regarding the lifetime. So these steam traps could become rather long. And yes, last year I found some which was more than 60 years in operation, and that is a long lifetime. Looking to the bimetallic steam trap, we have still the version from 1970 in some customer refineries which were working. If the condensate is clean, the filter is not blocked anyhow, we have no water hammer, then also this type of steam trap has a very long lifetime, and because of its subcooling up to 25-30 degrees Kelvin distance to the saturation curve, also the leakage of steam is in the first years more or less zero. The capsule type steam traps working very fast, are very close to the saturation curve with only 10 Kelvin below, working the first years without any loss of live steam, but then by the reaction time, it could happen that a small amount of losing of steam could be happen. If we look for the inverted bucket steam trap, we know we have a constant leakage, which is more or less 0.8 kilograms per hour. And if we're looking for the thermoelectric steam trap, we know they will increase in losing their live steam, increase because of the leakage which happens to the seat area. Orified steam traps are some which has banging up condensate. If they are designed in the wrong way, they can work correctly for a very short moment, because then the operating data changes and then we have a loss of live stream because we have summertime or not a process anymore, and so I don't consider this steam traps too much. Well, if we look now, the question is now, how could we find the most useful trap for our application, considering that we want to save our money there? And that is the point we have to look for in this little seminar. Steam traps don't have a problem if they have a certain amount of condensate load. If we look here for the condensate load, as more the condensate load increase, as less the steam loss, which we see on the left side, will happen. But if we look for the small amount of condensate, where the steam trap has to be tight, then each steam trap works in a different way. In many applications, we run with a very small amount of condensate. For instance, in refineries, the tracing or the drainage of steam line in every plant is only a small amount of condensate. So in many tests we have measured what happens when regarding the steam loss for the different type of steam traps, and this example shows the difference is here in the low amount of load, that we have maybe 10 kilograms of condensate load, but the difference in the leakage is 0.4 up to 1.2 kilograms, and that makes a real difference. Much more interesting, but is what happens if we're looking for the next 5 years, what happens over a certain amount of time. The time factor is interesting. When the plant runs 5 years and we did not consider the aspect of dirt or water hammer problems, just only how the working principle is under normal condensate quality condition, the TD traps, for instance, the thermoelectric steam traps, increase the loss of live steam significant. This graph here shows the additions of loss in 5 years. Here we have a thermoelectric steam trap, bimetallic or capsule type steam trap. It increased a little bit over the years, but here the leakage over the seat that the plate is hammering always against, and the frequency of the trap will increase, and by the frequency increasing, you will lose more and more steam, is also possible to measure and is shown in this graph. Well, so the next point is we have then also to say cost of ownership. What means cost of ownership? That means the purchasing price, of course, and it means that you have also different costs during the operations. And that I want to show. Here we have an example of the prices, of course, just to show the level difference of the different type of steam traps. We can say that the thermostatic steam traps has a certain level, maybe 250 euros in average. Thermal steam traps are much cheaper. Without filter, maybe down to 100 euro. And wetted bucket steam traps are wetted bucket steam traps are going up to maybe 300 euros. Ball float steam trap, which have the air venting and the ball, cost you 450, 500 euro. If we compare flanges DN25, for instance, it's only example. In the world, the price of course differs a lot. The cost of ownership are not only the purchasing cost and the operating cost additionally. Because when a project is coming up, very often the purchasing price is the point where managers want to save money. What costs appearing during the operation is quite not important for getting the order. But in the time of it changed to more important aspects in the world, saving energy, reliability, saving CO2, and the easy maintenance is also very important to have the possibility to interchange the steam traps if it's necessary. This spreadsheet here now shows how the main types of steam trap can be compared under consideration of purchasing price and operating costs. The influence of bad steam and quality and the bad design of the plant is not included. We say it's everything fine. So we look for an operation time of 5 years, 800, 600 hours a year. Steam costs are rather low. For petrochemical industry refinery, we consider 20 euro per ton of steam. We have to say you need round about 700 kilowatt hours per ton of steam, and then you can calculate that you need round about 65 cubic meters of natural gas, or you need round about 50 liters of diesel oil for 1 ton of steam. You can calculate your steam price by your local cost of this. Or smaller companies which have just a steam boiler to heat up something like a laundry, like a milk industry or pharmaceutical industry, they have to calculate today with 40 euros per ton of steam instead of 20. But I take just the refinery steam price. Condensate load should be 5 kilogram per hour. The drainage of the steam line should be considered. We can use the bimetallic, the capsule type, the thermodynamic type, inverted bucket type, or the ball float steam type. These are the purchasing prices. Here are listed the steam lost over the years. Thermostatic, bimetallic, more or less zero in the first 5 years. The same with the capsule type. Increasing of steam loss with the thermodynamic steam trap is a lot. I put the numbers in here, and here we have the content steam loss of the venting orifice of the inverted bucket steam trap, and we can say that the ball float steam trap on normal condition has no steam loss. At the end, we have a certain amount of loss calculated in tons. The tons multiplied with the steam price we mentioned here means additional cost for the operation, and now the total operating cost of the steam trap in the first 5 years of the operation. And we see that the thermostatic steam trap and also the ball float steam trap has a certain level of price, while the thermal steam trap becomes really expensive and the inverted bucket steam trap medium expensive. That means if this is factor number 1, we need the thermal steam trap is 8.5 times more expensive in 5 years than the bimetallic steam trap. Or if we look for the amortization, we can say we need only 6 months that we have an amortization from a thermostatic steam trap comparing with the thermal steam trap. I think that is really interesting to us that we have this time factor in such a short way shown here. So that the first part of the cost of ownership, I want to explain that the steam loss of a system is very important for the operation cost. On the second part of this presentation, I would like to speak about the cost of maintenance. Make it sense to change the steam traps, or would it be a good idea to change it every 5 years, the internals? And shall a customer make a supervision every 6 months, every year, or every three years only? Block trap are normally indicated very quickly that the product will not be heated in a sufficient way. That is not a problem. To improve the problem, is recommended just to clean the strainer of a thermostatic strap every year once. It's just a recommendation. Especially if you have a seasonal operation and during the summertime you have not a heating process, then you have oxidation by air and corrosion during the summer, and in the beginning of the autumn you find your problem. And don't forget, a steam trap is a control valve which works with a rather high pressure drop and a small lift of its orifice. And this, of course, always is a sensibility for dirt. If you have a 365-day operation, 24 hours a day, then normally we have no dirt problems, because then no corrosion appears, because no oxygen is inside the system. The on-off systems are a main problem. But if we have block steam traps, of course there is a little danger for the process, especially for the ability of the production. Much more important if you have this in a power plant. If the steam line is not drained correctly to the feed the turbine, then you got water to the turbine, and then you are facing a really big problem. But anything else is not so important. If we look for the cost of ownership in view of the yearly supervision, we have now to look or to consider the lead of loss of live steam. Live steam loss increase the need for feed water, live steam loss increase the cost of water additives, and the fuel or gas consumption for the burner increase, and CO2 exhaust will lead to a higher environmental pollution. And this is what we have to consider what happens there. Means increased if the steam trap lost steam, then we have the increased wear of the trap's seat due to the two-phase stream. Under a pressure drop of 40 bar, it takes only 1-2 weeks, and the steam trap is more or less full open, and we have a real problem, the condensate line. If we have a smaller amount of pressure, then it could take 1 year, 2 years, that orifice which cannot close anymore have these erosion problems, and then also the erosion problems in the piping behind the steam trap. The pressure can increase in the condensate return line, and this influence all other steam traps in the plant, that they maybe have not the capacity anymore, because the pressure drop is lost because of the pressure increasing in the condensate system, and that also normally returns into the increase of danger of water hammer in the condensate system. And so it could be said at the end that the traps losing steam reduce the availability of our production process. If we now look for the next slide, I would say this overview shows just in details which enormous money we speak about. Either the number of failed traps are only a little. Change the, you can of course change the steam price here to 40 euro, which if you have only a small plant. If you are in a petrochemical situation or refinery, then you take 20 euros for this. Steam losses which we can measure with our ultrasonic system, which we offer to measure the loss of steam, starts really good in a way of 2 kilogram to 3 kilogram, then we can say there is a real loss and a problem with steam trap if we have this amount of loss of steam, 2 to 3 kilograms. But if we take these three numbers together and we have 140 steam trap, then the steam lost in 1 year is already 26 tons. 26 tons multiplied by 20 euro are 560 euro loss of energy in the first year. And on average, we can say that maybe 10% of the steam traps in the plant have a problem by steam loss. So if you have 500 steam traps, then you have 50 steam traps, which offers you after 1 year problem. And this means 50 steam traps are already 25,000 euro of loss of steam in the first year. And here we can see how important it will be to make an annual check of your steam trap if they work correctly or did they have a problem. Just to say, steam trap survey. Should I do a steam trap survey every year, every 6 months, or every 3 years, what we asked before? Then we make, after a certain time, a survey when a customer planned, which was not done the last 3-5 years. Then we find out that around about 15 to 20% of the steam traps are already faulty. If we make an annual test, then we reduce this number to 5%, 5 to 10% of faulty steam trap, mostly caused by dirt and solids and corrosion problems in the customer plant. And of course, we also look, if we look for, and make a survey not for only steam loss, also for banking up. We measure the temperatures in the steam trap, and when we find out that it's not a temperature close to the saturation temperature in this customer field, then we also find out that the banging up of condensate can lead to poor process quality, unsafe condition, water hammer. So we test also then the right steam trap for banging up and so on. Well, sorry, that was the wrong direction. So, will we just look for some numbers? If we say we have a plan where we have installed 3,000 steam traps and we make no regular maintenance, we just let run the trap without any work on it. It saves a lot of money from the maintenance. We have the same steam cost, the boiler water cost, the working period should be 355 days a year. We have 20% of failed traps after 3-5 years. That are 600 pieces from 3,000 pieces. The average of live steam loss is 3 kilograms per hour per trap. Then we can calculate what is this in money. This are around about 1.8 tons per hour, 1,800 kilograms per hour. In 1 year, it's 15,336 tons per year. And that means at the end, multiplied by our steam cost, we have 352,000 euro each year, which we lost on energy. And that is often not considered that this amount of money is so much by a small numbers of steam trap which are faulty. So just these customers must be aware that something is really problematic there. And if we make a different way and say, no, we make an annual test of our steam traps, we want to find out which are the faulty steam trap, we build in a new regulator, a new bimetallic regulator, or we clip on a new capsule on this, or sometimes also an wall float trap regulator maybe, then we can say we have the same company with 3,000 pieces of steam traps installed. The annual steam trap is 10%, which we find out. With the ultrasonic check, which are offered by our opcos everywhere in the world, it needs round about 2 minutes per trap if we make it regularly. The cost of a repair kit, bimetallic regulator, a capsule is an average 140 euro. Time of repair of this 10% of steam traps is 100 euro. And so we can calculate the time for checking is 100 hours, the time for repair is 75 hours, and the time cost, I take 100 euro per hour of labor costs here in, maybe in Europe normal, in Asia a little bit less, I don't know. That means at the end we have spent for the total maintenance 60,000 euro, comparing, remember the other one was 352,000 euro. That means we have a saving possibility of 290,000 euro in this plan. And this is cost of ownership, I would say, that we also should not forget. If we make something, we have to make an annual check of the steam trap by an ultrasonic device with the help of the GESTRA opcos around the world. And we can say at the end, this steam trap survey will have an amortization in around about 2 months if you order this check of the steam trap. Hopla, what happens now? Yeah. Well, we can say since 1902, we are the specialists here in to improve the plans, and we hope we give you some ideas how you also can save some money. Well, this is since 1902, and I would just now ask Kwang, the GESTRA sales manager in Singapore, to take over, and he had a look at for the last 1 hour 50 minutes for any questions, and of course for the final word. I thank you very much for your concentration, dear audience, for all over the world, and hope we see us again in the next seminar session with GESTRA Singapore. Goodbye.
Yeah, thanks so much, everyone. I am Quang Nguyen. I'm sales manager for Southeast Asia. Thanks so much, fantastic feedback, and we also have so many questions. So now we will moving into the question and answer. Please type your question in the chat area. Please put your name next to it. If we cannot answer during the presentation due to the time constraints, we will follow up with you via email. So for now, I will pick some random question, and then we will have some answer. So the first question is that I think this question is coming from India. How would large volume of steam in fixed orifice can be stopped from passing in the orifice device? So as you see from the Marcel presentation, for fixed orifice device, when you select the fixed orifice device, you have to select based on one of two conditions. The first condition is that you can select based on the startup load. So when you as you know, the startup load normally is larger than the running load. So when you choose the orifice device on the startup load, the orifice size can be a bit bigger. So when you go into the normal running load, the orifice size become too big, and it can have big steam leaking. The second method of choosing the orifice device is that you choose based on the running load. So when you choose based on the running load, in the startup, the orifice size become too small. So the condensate will be banking up, and this leads to how can I say, it makes the startup time will be longer, and it will affect to the process. So sometimes you can hear some noise and water hammer. So therefore, orifice device is only used when you have quite constant load and the quite constant pressure, as mentioned in the Marcel presentation. If you have the fluctuation in the load and in the pressure, we recommend you don't use fixed orifice device. especially in midnight drainage and especially in the heat exchanger application. It will affect heavily to the process, or it can lead to the steam leaking. Yeah, and then the second question I want to pick up is that I think this question is coming from Vietnam. What is the application of steam trap in power plants? So as you know, in power plant, you can use steam trap in several areas. One of the first area you can use is in the midnight drainage. And then the second area also you can use is in turbine drainage. So normally in turbine drainage, you will install the steam trap in parallel with the control valve. So the control valve will work in the startup or in emergency mode. And those steam trap we work in the normal situation. Yeah, so that is some of the application in power plant. Actually, next week we will have one section on power plant, so you can join on next week presentation, so we can talk more detail about this in power plant. And then now I will turn over to Marcel and Heiner to pick up some questions to answer for audience. And Heiner and Marcel, turn over to you.
Yes.
Okay, Quang, thank you. Marcel, can you start, please?
Yes, just give me a second. I will, yes, just keep it at that. I'll just, hi everyone. So yeah, there are plenty of questions now. So I just saw 33 now. We have not published all of them, so you cannot maybe not see them, but we see them and we can answer them for sure. Maybe not all of them now, because 33 is quite a lot, and sometimes the answer is takes a few minutes. But we'll pick a few and we will answer the questions we haven't answered yet now in the live session right after that, so that you for sure get your answer if you like. And I will just pick a few, maybe from the older ones. Let's say, how full condensate heat is utilized by banking up? Thank you, Mr. Ajit Kumar. Yes, you can also use the heat of condensate when we have this banking up. This is so-called a hot well installation. So we have, let's say, two heat exchangers. The one will work with steam, and the other one below will work with condensate. So the condensate coming from the first heat exchanger will operate the second heat exchanger, which will work with condensate heat, which is of course less, but we can preheat the product in the condensate heat exchanger before we enter with that inside the, let's say, steam operated heat exchanger, which is the so-called hot well operation. It's absolutely possible to do it that way. And there are two different kinds on how to operate a heat exchanger. You could do it only, let's say, by steam control. So you control a control valve that will, let's say, control the amount and the pressure of the steam entering the heat exchanger, or you can do it with, let's say, a level control in the heat exchanger. They are usually in an upward position. And then we just control the condensate load inside the heat exchanger, and thereby we control the heat that we transfer to our product. So this is something that also works, but then we have, let's say, a temperature indication at the outlet of this kind of heat exchanger, because we want to measure, let's say, the temperature of the condensate, because if it gets too cold, we have to open it and release the condensate so that, let's say, hotter condensate come and steam can come to the heat exchanger. So this is, let's say, a way how to use condensate heat. Second question, are ball flow type traps repairable? Yes, but it depends a little bit on, let's say, what happened there. If we have a problem with the body of the steam trap, then it's not this simple, of course, because then we have to change the whole trap because the body is damaged. But this is the less common case. If we have any problems, then usually it might appear on the control unit inside, and this part is replaceable. So we can just open the steam trap, and then we just replace the control unit, but it should be the same like we used before. So like we can get this information from the nameplate, so then we know what was the size of the orifice, and yeah, the maximum differential pressure is the information that we need to calculate the size of the orifice, and then you can replace it. It's possible. But you cannot, let's say, replace only the ball. So this is something that you should not do by yourself, because it should be, let's say, one unit that was tested in our facility to guarantee that it's working totally fine. So if you change something, it's either the body or the control unit or the whole device. So let's take another question. How steam trap handle pressure and flow rate fluctuations? So the ball float steam trap does it as I shown in the first part of the presentation, by the level. So the higher the level gets, the more of the orifice will be opened. And if we speak of, let's say, the thermostatic steam traps like the BK and the MK, they also work at different pressures, because let's say, the conditions that we have in the system, like the pressure and the temperature, when that change, also, let's say, the behavior of the liquid in the membrane type capsule will change. So if we increase the pressure, then the evaporation temperature of the liquid inside the capsule is also higher. So this is how we can use one and the same steam trap for different pressures. So it will directly go the way along the saturated steam curve. Same with bimetallic forces. So they don't work only at one pressure and one temperature. So also bimetallic forces are changing depending on the pressure. It's just thermodynamics. And this is how they change their behavior. Yes, so you will get the record of the webinar. We made a record here, and we want to provide you with that.
Do we want to transfer over to Heiner? Heiner, you want to pick a question?
Yes, thank you so much. I just saw that there is a question: what are the normal troubleshooting a thermostatic trap and ball flow trap? Troubleshooting is really on thermostatic steam trap that you make an annual test by an ultrasonic design. Well, what we can do continuously is to install a sight glass which is able to show that there is an leakage of steam or bringing up of condensate. That is in our normal product program. So-called vaposcopes are able to show exactly what happens inside the steam trap. They must be installed in front of the steam trap, because behind the steam trap we have flash steam, and the flash steam is not indicating the right working principle of a steam trap, but that is what we can do there. What I said in my seminar, I recommend once a year on a thermostatic steam trap maybe to clean the strainer is important. And then I want to talk about the supervision of steam trap with an ultrasonic device. This is only possible if you have not more than, I will say, 100 kilogram per hour condensate load, because with a higher condensate load, then you have all the noises, the internal noises in the steam trap caused by flash steam, and so the ultrasonic possibility is not possible anymore. There we have to use this vaposcopes, the sight glasses, if we have a larger amount of condensate. But most of all steam traps, I would say more than 95% are working with smaller amounts of condensate. And there we can really find out very good with this device what happens inside the steam trap. Is there a normal closing moment that steam trap must be quiet, or is there a continuously noise internally which we can consider out with the ultrasonic device and can say there is a problem, there's a leakage, and then by the level of noise we can say more or less it's between 2.20 2.53. It is not possible to say the steam trap has a leakage of 3.815 kilograms per hour. That is not possible with an ultrasonic noise detection. But a roughly idea what is the amount of condensate of steam loss we can do with this system. That is what I want answer to this yes question. So back to Huang.
Yeah, so here I also see a lot of questions. Yeah, I think close to 40 now. For example, one question is that which type of steam trap is most commonly used in industries and why? So yeah, so I think you also go through several steam trap, different types of steam trap for Maxell. One of the most common one is bow float trap. Yeah, so this is one of the most common one. Besides that, you also have the thermostatic steam trap, because thermostatic steam trap have almost zero leakage. So that's also one of the most common one in the industry. I think the most important one is the application. You have to see what kind of application, and then we can recommend the most suitable steam trap. So actually in GESTRA we have one book we call that is condensate manual. So in the condensate manual book we also recommend what kind of application, which steam trap you should use. So if you are interested in that kind of book, we can send you by email. So please reach out to us. So we will make sure that we send you a copy, the e-copy of the book, so you can refer to the application for steam trap. Maxell, do you want to pick any question, Maxell?
Yes, I can do that. I will just bring myself on the screen now again. Just give me 1 second. Okay, so what do we got? Which is more economical, an MK or a BK? That's quite an interesting question, because this is hard to say. An MK and BK have more or less the same price, but whether they are economical or not depends whether they have steam losses or not. And from the beginning on, they won't have any steam losses. Maybe after a while. I think the right question that we should ask here is the right steam trap in the right application? And if I have enough space for banking up of condensate for streamline drainage, I would recommend the BK, because it is, let's say, more resistant against wear. It is, let's say, it has less opening and closing frequency, because it has more banking up. So this is another reason why it lasts for up to 15 years. And the MK, let's say, is the right one if we have not that much space that we can use for the banking up. So when we speak about economical, it very much depends on the application that we have here. And referring to this, I would like to speak about a second question I have here. So I will just read it for a moment. I have BK28 high pressure bimetallic steam trap, which I installed since 2015. For my 65 bar G steam lines, what type of maintenance needed for this trap? As I observed, it is functioning till today and I never opened it to check. Yes. So to open and to clean it is just, let's say, a recommendation in our manuals. But as long as it's working fine and you know that it's working fine, then you can just keep it as it is. So never change the running system is the right statement here. And this is why I would say you should test it every now and then, so that you really know, okay, when we have problems, then I can immediately find it out via ultrasonic testing. So we have the VK P41, which is the testing device, and only by doing just by doing a very fast, quick check, we can really precisely find out whether the steam trap is still doing its job or not. And if you do this once a year, you don't have to open it, or you can just rely on it, because we have immediate results from the testing, which is a good thing to guarantee that your process is working fine. I'm maybe looking for another one. Yes. Okay, so some customers ask for steam loss from the steam trap. So is there any chart to calculate the steam rate through these traps? Yes, this is possible. You can, but you have to figure out how much steam is leaving through the steam trap. This is something that you can, let's say, only estimate with the ultrasonic device. So you will get a rough estimation how much steam you're losing there, and it's beginning from 3 kilograms per hour, which is like nothing. This is impossible to measure. There is, let's say, a possibility to calculate how much steam we are losing if the steam trap is open 100%. So there's a formula for that, and we can do calculations on that. So if that is an information that is useful maybe for your calculations, then we can do it. So it's only possible to calculate it when we think about this extreme conditions like fully opening and just from the very beginning of the steam leakages. In between, it's not this simple to calculate the right amount. It's just estimating. So,
okay.
Yeah.
Okay. Should we have, I think we have time for one more question, and we probably should wrap up. So who wants to take one more question?
Okay, I think I will hand over to Heine to answer just a last question before we are closing the session here right now. But as we said, don't worry, we will try to answer the ones that we have not answered yet, so that everyone gets the information that he or she needs.
Correct.
Well,
all right, great. Thanks, Marcel.
Mm-hmm. Thank you. Yeah, just I read just here one question, which is for bucket type traps. The steam will lift the bucket and plug the closing unit orifice in the upper position. How will the bucket be back to the original position so that condensate will pass through the orifice? Well, we have, like Frank has already offered, we have this little manual where we explain all this function a little bit of our steam traps, and could be shown there very quickly. For the inverted bucket steam traps, yes, we have the same pressure inside the housing, and as soon as the steam will condense under the bucket, then the weight of the bucket is falling down. That difference is that the bucket will open again, then the condensate is discharged, and the condensate is passing through the orifice. Steam will enter under the bucket, lift up the bucket, and will close it. Now we have to wait again until the steam in the bucket is condensing, which will happen after a certain time, and then the bucket can open again and discharge again the condensate. And there you see already a little different. A ball float steam works continuously all the time with the same amount of condensate. An inverted bucket steam trap must work on, off, and that is also part of the lifetime, that the inverted bucket steam trap will never have such a long lifetime like the ball float steam trap, which always is on the same position inside the housing and will not move as much as any other type of steam trap. But as I said, really it is wonderful to have so much question, and we will answer this time, of course, all by time. I'll give you the right literature to read it a little bit, and then you understand the system very well. Or you come to Bremen and make a seminar on our facility. That also you're welcome there. Okay, back to Hedda, please.
All right.
Very good. Very good, very good. Thanks. Thank you so much, Marcel and Heiner and Kwang as well. Thank you all for answering questions and presenting. I hope everybody enjoyed. I hope everybody learned something. As you all probably know, that this is a first seminar in series of 3. We have next week, we will hold in a similar fashion seminar on boiler controls, and the following week we will have on a power generation, and then following week will be boiler controls. So I really sincerely hope that you will be able to join us again, and I hope we can continue with these webinars that have been beneficial to you. As my colleagues shared with you, we will answer the questions that we didn't get to today. We will follow up. And we will also appreciate if you could help us with a survey. We will follow up with the survey so you can give us your feedback on this session so we can make improvements going forward. With that said, thank you everybody. Have a wonderful day, and we see you again next week.
Okay. Bye-bye.
All right.
Bye-bye.
Tschüss.
Bye-bye.
Auf
Thank you so much.
Wiedersehen.
Bye-bye.
Bye.
Bye, everyone.
Bye.
So, Marcel, jetzt musst du live ausschalten, wenn wir wieder intern sind.
Dann mach ich das mal.
I'll click the end button.